In this video, we are solving a small problem based on the concept of laws of stretched strings. Let me read out the problem for you. A sonometer wire has a length of 114 centimeter between two fixed ends. So, before going anything further, let me first explain what is this sonometer is, and then I will come back to the problem. Let me explain what do you mean by sonometer is. I am drawing a diagram in a two dimension, but the sonometer consists of a wooden box like this. Assume there is a wooden box. It's a wooden box. On that wooden box, there will be a kind of a stand. To that stand, we will arrange a wire, light-weighted and extensible wire, like this. At the end of that, there will be a pulley, and the wire will slip over the pulley. At the bottom of the pulley, we apply a load, mass M. So the load mg acts in downward direction, and in the string a kind of tension is generated. So because this end is fixed, this end is loaded, this wire behaves like a stretched string. So what all the rules that we have developed for a stretched string? We have derived an equation for the frequency of a stretched string in the other video, in the previous video, as P by 2L, where P is the number of segments, root of tension by linear density is valid in this device, sonometer. Why do we use this sonometer? We can use this to experimentally verify laws of stretched strings. What are the laws of stretched strings? They are very simple. They are all derived from this equation itself. See, from this equation. When tension and linear density are constant, frequency is inversely proportional to length of stretched string. When T linear density are constant. These are very simple laws. This is called law of lengths. When length and linear density are constant, frequency is directly proportional to square root of tension. Simple. When length and tension are constant, frequency is reciprocal of linear density. These three laws are called laws of stretched strings. These three are can be verified using this device called sonometer. We can also use it to find frequency of a tuning fork. We can use a tuning fork and find its tuning fork frequency using this device. Well, how do you do that? We'll leave it because the post becomes too lengthy if I go into that discussion. But here what we will do is, on this board, on this wooden board like we have said, we get a tuning fork. We keep a tuning fork, vibrate the tuning fork and keep it on this wooden board. Then that vibrations will pass through this from this wooden board to that wire, and then this wire also starts vibrating. So here we keep a bridge called something like a movable bridge. Here also we'll keep one more bridge which is called a movable bridge. So these two are movable small wooden bridges. And on the wire in between the bridges we keep a small paper rider. So in principle, when f of fork is equal to f of wire between the bridges, frequencies are equal, they are in resonance, therefore it vibrates a lot and the paper rider falls off. That's an indicator. This is how people do experiment. Probably you have done this experiment in the laboratory. That is the principle that we are talking about. And of course, then now we'll come to the problem, right? Now what he is saying in the problem? Where shall be these two bridges has to be placed. So he is asking about the location of these two bridges, so that it divides the wire into three segments of frequencies in the ratio 1 is to 2 is 3 is to 4. So if you notice little carefully, this is divided into three segments. This is segment 1, this is segment 2, this is segment 3. It shall be divided into three segments in such a way that the ratios of frequencies must be equal to 1 is to 3 is to 4. That's what the given question is. So if I take this law into consideration, frequency into consideration, here tuning for tension in the load is kept constant, therefore tension is constant. Wire has not changed, therefore its linear density is constant. So as per this law, tuning fork is inversely proportional to length of that wire. That's called law of length in stretched strings. N is inversely proportional to L. So I can say N1 is to N2 is to N3 is 1 by L1 is to 1 by L2 is to 1 by L3. They are reciprocal. Or L1 is to L2 is to L3 is 1 by N1 is to 1 by N2 is to 1 by N. That is 1 by 1 is to 1 by 3 is to 1 by 4. So if I want to write it like further as a ratio, 12 is an LCM, therefore multiply with 12. 12 is to 12 by 3 is to 12 by 4. That is 12 is to 4 is to 3. So it shall divide the wire into three segments, having the lengths in the ratio of 12 is to 4 is to 3 out of total 114 centimeters given for you. So for what is being said to happen in a given problem, the length shall be in the ratio of 12 is to 4 is to 3. This 114 has to be divided in this ratio. Now I can say L1 is 12 times of how many parts? 12 plus 14 plus 3. That is 12 plus 4, 16, 16 plus 3, 19. 12 parts of 19 parts of the total length here. L2 shall be equal to 4 parts of total 19 parts of L. L3 shall be equal to 3 parts of 19 parts of the total length here. So I can calculate this further. 12 by 19 of total length is 114. 19 sixes is the 114. That is 72 centimeters. L2 can be found as 4 by 19 of 114. This is again 6. 6 4 is 24 centimeters. LB can be found as 3 by 19 of 114. This is same 6 18 centimeters. So the wire shall be divided into three segments in such a way that the three segments shall divide. So if I draw a wire for you, yeah, I'll just draw it for you. Just the same diagram again. It's the fixed thing. This is L1. This is L2. This is L3. That shall divide the total wire of length 114, three segments of L1, L2, L3. L1 is very clear, 72 centimeters. L2 is 24. Be careful. From L1 to L2 is 24. From here to here is 24. That means from the beginning, if you say from the fixed point, that is 72 plus 24, that is 96 centimeters. So where shall we play the bridges? Bridges shall be kept at, from the beginning, one bridge at 72 centimeter and second at 96 centimeters. This is how we have to solve the problem, but to solve this problem, we shall know the concept of sonometer and how it works. Hope you understand it, or you can listen to this once again to get it right. Thank you. Thank you for watching.